Well, welcome back again. I'm back in the shop working on the Triumph Spitfire tachometer. And before I get started here, some quick corrections from the last videos. I actually shot both videos at the same time, so this is the first update since I finished the first round of playing with this. First off, I decoded the color codes and the capacitors, and I got for brown, black, yellow, black, red, and you read them from the top, the farthest away from the leads, down to the bottom base where the leads poke down. So get this open without breaking anything. So you read from this side down. I got 0.1 microfarads and 22 nanofarads, where the first two colors are the digits, then the multiplier, tolerance, and voltage range. They vary a little bit from brand to brand and type of resistor you're using, or sorry, capacitor that you're using. But Mr. Mike Burr happened to send me a message on the very first video, if you go look in the comments section, with some links to some schematics of these little tachometers, and looking at the schematics, they did indeed show 3 22 nanofarad caps and one microfarad cap, and also the resistor values that I was able to measure, the 150 and the 46.6K, do match up with the values on that schematic, which were 140 and 47. Oh, I also had this 32, which is a 33K. So all in all, that looks like I have a valid schematic of this little circuit board. Some other corrections. I had some rubbish in the last one about thinking this might just be an op amp and some filtering circuit. It's not. It's a voltage to frequency converter chip. Also, the bit about the dwell delay being time based, it is not. It's degrees based. Most dwell times will be listed in degrees. For some reason I thought this one was listed in milliseconds. I guess just going nuts in my old age. So the whole bit about the duty cycle changing with RPM is complete and utter bogus. For any given RPM range, the dwell time is the same number of degrees over the total degrees, so therefore the duty cycle is exactly the same for everything. So I think that's all my updates. So now on with trying to repair this little bugger. So this is a nice little voltage to frequency chip. We have a series of caps. Reading some of the forums that Mike linked to me, one of the biggest problems was this little electrolytic going bad. So I think the first thing I'm going to do is just strap a different electrolytic across it, one that's hopefully a little newer than 1977, and see if I get better operation out of this thing. This electrolytic cap is basically just part of the voltage filter / regulation circuit. I was not able to find a data sheet for this chip, so if anyone out there has a data sheet for M7714 MIC2 or M1C2, I've seen it listed both ways now. I'd be really interested to see exactly how this little chip works and what's going on. The replacement voltage to frequency chips I have on order have a built-in Zener diode on the power input. So I'm kind of wondering if this chip does as well, so where is it? So this resistor here plus a Zener diode inside the chip acts as a voltage regulator to set up a fixed voltage across this cap that's something less than the 12 or 14 volts it's getting put in. Sorry for the delay, I'm sort of failing at finding a 47 microfarad cap in my random bin of capacitors here, so I need to go to a different random bin of capacitors. Oh, here's a 33, that's close. Oh, 47 microfarads, 16 volts. That'll do me. And since that just came out of my super random bin of crap, quick pop it on the meter and make sure it has yeah, 53 microfarads. That's about right. And leakage. Ooh, that's quite a bit of leakage. Let's see if that's in the acceptable range. 10 volts, or sorry, 40, 50 microfarads, 10 volts, 25. Nope, that one's bad. Yeah, that one's toast. $220, 33, 33. Okay, this one's leaking down slowly to about where I'd expect. Yeah, he isn't good. Value-wise, about dead on. So go with that. While I got everything powered up, I might as well test the rest of these quick. The ceramics, I'm not so much worried about leakage, but I do want to just quick test them and see if they're within the right value. Typically when they open up, they lose value before they start leaking. Well, due to their construction, leakage is usually not a problem. Uh-oh. Just have to get some jumper wires out to get that attached. There's 1, 2, 3, and 4. No polarity on these, so it's just clip on and test. It's supposed to be 0.1. It's right there, so that one's good. And these are all 22s, 22 nanofarad, not microfarad. So picofarads, nanofarads, so 20.4, close enough. .9, again close enough. .1, yeah. So these were, oh, these are plus or minus 20%, so yeah, totally within spec. And typically with the ceramic, I think these are ceramic, polymer, whatever, caps like this, I don't usually see a problem with them unless they're physically damaged. The epoxy coating on them has chipped on the corners or on the ends. I don't think that's an issue. I've seen it on them before. It's never been a problem. So I'm just gonna try and this back up quick. These back up quick. Just sort of. There's one. There's two. There's number 3. A little solder on this guy. A fresher little electrolytic cap just to try. I just need a little chunk of wire. Yeah, good enough. Not very sexy, but it'll work. Okay, so we got that all tweaked together. Before we get started here, I want to get this guy out so we can poke around and see if we're getting all the signals we're supposed to be getting. Power brick. Okay, scope. Turns on. Also, I looked at the crank on the ignition system, or crank and ignition system on this car, and the pistons are 180 degrees out of phase of each other. So in this particular engine, 1 and 4 are up at the same time, and 2 and 3 are up at the same time. And 2 and 3 are 180 out, so they're fully down when 1 and 2 are up. So there should be 2 ignition pulses per revolution, not the 4 I originally set up for. So let me get that fixed up here quick. So 4,000 would have given me 2,000 RPMs. So I'm going to drop this down to 2,000, which should give me 1,000 RPM. And the first thing I'm going to do is just hook this up real quick and make sure my generator is actually putting out what I think. So 5 volts per division, 5, 10, oh, almost 15 volts. Ten to 1 probe. Okay. Something's off here, because that says 8 volts per division, and I'm getting 16, or 8 volts middle line to peak, but I'm seeing 5, 10, 15, 16 volts if everything's set up right. It's in the range I want to be, so I'm not too concerned, but it's more strikes against this meter being going on the fritz. I've had this thing for forever. I think it was built, calibration sticker on it. It was calibrated in last in 93, so it's at least, you know, from 93. Backlight's dead, and other bits and bobs have all started to flake out on it, so I gotta be a little careful when I use it, because sometimes it's not truly telling me what's going on. So I'm just gonna go a couple pulses on the screen, and then go cursor data, function, 1 over dt. And then just double check my frequency quick. Yep, about 2 kilohertz, so yep, that works. And since I'm in here, peak to peak, yeah, see, this is reading 16 volts peak to peak, where it's only putting out 8. A factor of 2. These are my 10 to 1 probes. Yep, 10 to 1. So there's a factor of 2 off, either in that guy, what he's thinking he's putting out, or in this guy, which he thinks he's reading, and I'm guessing it's this guy. 9 volt battery. That's a pretty easy way to check it. Minus, plus,